So let's do this. So we've talked about how we can evaluate indefinite integrals. Indefinite integrals are just kind of undoing the derivative process to find the original function whose derivative would give us that particular function as, whose function would give us that particular derivative. What we haven't, and we've also talked about definite integrals. We said that a definite integral is something that gives us the area under the curve or the graph of f between two particular x values, x equals a and x equals b. And we were able to evaluate some of those definite integrals by using geometric formulas if that region just happened to fit like a geometric region that we have some kind of formula for. But we started by looking at the graph of x squared plus 1. And we were trying to estimate the area under that curve between, what was it, between 0 and 2. You guys remember doing that? And so we tried to approximate it using Riemann sums. And we came up with the idea that if we had lots of rectangles, we get a good approximation. And theoretically, if we could get an infinite number of rectangles in there, we would have the actual area. But we still don't have a way of evaluating what that actual area would be. So that's what we're going to talk about today, is the fundamental theorem of calculus. The fundamental theorem of calculus is our way of evaluating the area under a curve of a graph who doesn't fit a geometric formula. So if f is a continuous function on a closed interval from a to b, then the integral from a to b of f prime of x is equal to f of b minus f of a, where f is the antiderivative of f prime. So in other words, if we want to evaluate the definite integral between two x values for some function, we would take the antiderivative of that function, just like we were doing when we were doing indefinite integrals. And then we would evaluate that function at the point where x is b. We'd evaluate that function at the point where x is a. We'd find the difference, and that would be the definite integral, the value of the definite integral from a to b, the area under the curve of that graph between x equals a and x equals b. Okay, let's see what that looks like. We want to integrate x squared plus 3, but now we have these bounds. We're going to do that from x equals 1 to x equals 2. In other words, we're taking the graph of x squared plus 3, and we're finding the area between that graph and the x-axis from x equals 1 to x equals 2. Well, that would be a parabola shifted up 3 from 1 to 2, which, as we discussed before, doesn't fit a geometric pattern. But if we can find the antiderivative of this function, and if we can evaluate it at x equals 2 and x equals 1, we can find the actual area and not just an approximation using a Riemann sum. So let's start by finding the antiderivative. So if I take the antiderivative of x squared, then I'm going to get what? X cubed divided by 3, the antiderivative, not the derivative. We're undoing it, right? Because if I took the derivative of x cubed over 3, I would get that x squared. Plus, the antiderivative of 3 would be 3x plus c. So we take the antiderivative of this. Now we want to evaluate that at x equals 2 and x equals 1. The way that we can denote that is using this notation. We're saying we're going to evaluate that at 2, we're going to evaluate it at 1, we're going to subtract. In other words, we're looking at f of 2 minus f of 1, not f of b minus f of a. So if I put in 2, then I have 2 cubed is 8 over 3 minus 3 times 2, 6, plus c. Then from that, I'm going to subtract that function evaluated at 1. Well, if I put in 1, I have 1 cubed over 3, so 1/3. Oh, plus 6, thank you. Should be plus. If I put in 1, then I have 3 times 1 is 3, plus c. So then I'm going to distribute the negative and regroup. I have 8/3 minus 1/3, right? Plus 6 minus 3, plus c, hey, minus that same constant c. Well, those cancel. 8/3 minus 1/3 would be 7/3. Plus 6 minus 3 would be 3. So I have 7/3, 7/3 minus 9 plus 9/3 would give me 16/3. And because that definite integral represents the area between the graph and the x-axis from A to B, what we're saying is that that actual area is equal to 16/3. So 5 1/3. The area between the graph of x squared plus 3 and the x-axis from 1 to 2 is 16/3. Exactly 16/3. No approximation needed, no geometric formulas needed, just the fundamental theorem of calculus. I want to point out something real quick. When we took the indefinite integral, we ended up with the constant of integration, the plus c. Well, if I take this plus c and I subtract this plus c, they cancel each other out. Do you think that'll always happen? If I'm taking this function and I have the plus c and then I subtract that function, are those always going to cancel out? Absolutely. So when we're evaluating a definite integral, not an indefinite integral, we don't have to put the plus c. Because when we plug in the bounds of integration, the f of b and the f of a, those constants are going to cancel out. So the time has come that we don't have to put the plus c, finally. Right? Finally. However, with an indefinite integral, you have to have it. But with the bounds of integration, you don't have to put it because those constants of integration are going to cancel out. So with a definite integral, we don't need it. You guys have any questions about that? My time has come. Okay, let's try another one. We want to integrate 3x minus 1 times x plus 2 from -1 to 4. Now, the way it's written, we would have to do like u substitution, but I think that the easier way to get around u substitution here would just be to go ahead and multiply it. So we'll distribute. That's the integral from -1 to 4 of 3x times x is 3x squared. 3x times 2 is 6x minus 1x, 5x, and the -1 times 2 gives us -2. Yep, the dx is there until we actually integrate it. By the way, one of the questions that I've seen a few people ask, and I don't know if anybody in here has asked it, but I get asked, what happened to the dx? Yeah. The way I think about it is like this. What happened to the square? It was undone by its inverse. Squaring and square root are inverse operations. They undo each other. So yeah, I think of it the same way. When I take the antiderivative of the differential, they undo each other. So just like we wouldn't say, hey, where did the squared go here? It's the same thing. It's gone because we did its inverse operation. So when we undo the differential, we get back to the function. When we undo the square, we get rid of the square. Same idea. Does that make sense? All right, so now we need to take the antiderivative of this. Antiderivative of 3x squared will be 3x cubed over 3, or just x cubed. If you need the intermediate step, write it. If you're ready to jump straight to x cubed, go for it. The antiderivative of 5x will be 5 over 2 x squared. Okay. Minus the antiderivative of 2 is 2x. And if we were doing an indefinite integral, we'd definitely put the plus c. But since we are going to evaluate that from x equals -1 to x equals 4, we don't have to put it because when we subtract, the constant of integration is going to go away anyway. So I need to evaluate this function at 4 first. I've got 4 cubed is 64. Plus 5 halves times 4 squared is 16. Minus 2 times 4 is 8. And then I'm going to subtract from that. -1 cubed is -1. Plus 5 halves times -1 squared is just 1. Minus 2 times -1 will be +2. So in here I've got 64 minus 8 is 56. And then I can reduce that. 2 goes into 16 8 times. And 5 times 8 gives me 40, so plus 40. And then over here I've got -1 plus 2 is 1, plus 5 halves. So I have 56 plus 40 is 106, but then I would subtract 1, gives me 105. 96, you're right. 96 minus 1 gives me 95 minus 5 halves. Need to go to the side and do a little scratch work to see where that 95 came from. This is 96 minus 1 minus 5 halves. So we'll get a common denominator. 95 times 2 is what, 190? Minus 5 would be 185 over 2. Well, what would be 184 would be 92 and a half. Yeah, 92 and a half. Okay, let's look at another one. So let's rewrite it. We have x minus 4 over x to the 1/2. And if I split that up, that's x to the first. So x to the first divided by x to the half is x to the 1/2. Remember that when we divide, we subtract the exponents. So 1 minus a half is a half. Do you guys need to see some work for that? Okay. What I'm doing there is I'm taking x minus 4 divided by x to the 1/2, and I'm dividing that like this. Because when we add or subtract, we keep the denominator and add or subtract the numerators, right? So we're okay with that. So I have x to the first and x to the 1/2. when I'm dividing, I subtract the exponents. This we could just make negative and bring to the top, right? So I have 1 minus 1/2 is 1/2. And then minus 4x to the negative 1/2. We good with that? Go ahead and bring it in. Okay, so x to the negative 1/2 dx. Now we have it set up as something that we can integrate. So the antiderivative of x to the 1/2 would be x to the 3/2 divided by 3/2 or times 2/3. The antiderivative of x to the negative 1/2 would be x to the positive 1/2 divided by 1/2 or times 2. We already have the 4 there, so then we would end up with 8. So we have the 4 times 2 that gave us that 8. We okay with that? So now we're going to evaluate that starting at 1, stopping at 9. So we have 2/3 times 9 to the 3/2 minus 8 times 9 to the 1/2 minus, we'll pause for the pledge. Everybody understand why that's just 2/3 minus 8? That's 1 to the 3/2 and 1 to the 1/2 are just 1, right? Okay, so let's talk about evaluating the 9 to the 3/2. Remember that the denominator means that we take the root. The numerator is the exponent. We could cube 9 and then take the square root, but I don't like doing it that way. I like to take the square root and make the number smaller and then make it bigger. So I've got 2/3 times the square root of 9 is 3, and 3 cubed would be 27. Minus 8 times the square root of 9 is 3. I'll leave this as 2/3 minus 8 for now. So I would simplify this because 3 will go into 27 9 times. We have 2 times 9 is 18. Minus 8 times 3 is 24. Minus 2/3 plus 8. Distributing the negative, right? So then 18 minus 24 would be negative 6, plus 8 would be 2. Minus 2/3 would be 6/3 minus 2/3 gives us 4/3. Any questions about that one? All right, you guys try the next one. looking at the definite integral from 0 to pi over 4 of secant squared x dx.